Absolute age dating. Before we can talk about absolute age dating, we have to remember relative age dating. Remember, relative age dating is age compared to something else. That's age in relation to something else's age. Geological features, other rocks. We talked about the layers in your laundry basket, your dirty clothes. The further you go down, the stinkier the clothes are, the older they are. The fresher clothes that you might can wear a second time are on top. Another way to think about this is take an elementary school kid, yourself as an eighth grader, and our school principal. If we put you all side by side, we could tell who was older, who was younger than who. You're younger than the principal, but you're older than the elementary school kid. The elementary school kid is younger than everyone, and the principal is oldest of all. But it doesn't tell you the exact age, only your age in relation to each other. Absolute age is precise, exact, like your age in years. If you say you're 13, the fifth grader's age and the principal's age, those are also absolute ages. When scientists want to determine a more precise age of a rock or an object, they rely on the study of a natural process called radioactive decay. And they use a procedure called radiometric dating to determine a more precise or absolute age. So, before we can start talking about radioactive decay and radiometric dating, we got to take another step back to the periodic table of elements. Remember that each element is made up of atoms, and an atom is the smallest part of an element. Each atom contains protons, neutrons, and electrons. All atoms of each element have the same number of protons. Always. Same number of protons. But some can have a different number of neutrons. If they have a different number of neutrons, it's called an isotope. Most isotopes are stable, meaning they behave like most other atoms. Nothing new. Same. But some isotopes are unstable. Unstable isotopes are radioactive. That doesn't mean they're going to explode or cause cancer, but they are radioactive isotopes, meaning they're giving off some kind of energy. These radioactive isotopes decay, and all that means is changing. So carbon-12 is regular carbon, 6 protons, 6 neutrons, perfectly balanced. But there's also carbon-14 or C14, still has 6 protons, but there's 8 neutrons. That's not balanced. 6 plus 8 equals 14. So it's not balanced, has a different number of neutrons than protons. That makes it an isotope. C14 is the isotope that we want to use when looking at organisms that have died in the last 60,000 years. I'll get to that more in just a minute. So, carbon. Carbon-12 is in the atmosphere, the air we breathe, as carbon dioxide, CO2. Carbon-14, C14, is also in the atmosphere, naturally. When an organism is alive and breathing and eating, the amount of C12 and C14 in that organism, like this horse here, is the same ratio, has the same amount of C12 and C14 as the ratio that you would find in the atmosphere and all other organisms that are alive. They all have the same ratio. But as soon as the organism dies and is no longer taking in C14, it's no longer taking it in by breathing or eating, the C14 starts to break down and no new C14 is coming in. So if C14 is changing into something else, N14, but the C12 stays the same, then that ratio is changing. There's less and less C14 and more N14. We know that carbon-14 decays at a constant speed. It's always the same. That carbon-14 is also called a parent isotope, as it decays at the speed of 5,730 years of a half-life. As it decays, that parent isotope of C14 turns into the daughter isotope N14. Just like parent cells and daughter cells, we're talking about parent isotopes and daughter isotopes. The parent isotope C14 decays into the daughter isotope N14. The same constant speed, half-life of 5,730 years. And a half-life, we'll talk about in just a second. Half-life is the amount of time required for half of the parent isotopes to decay into daughter isotopes. This graph helps to explain how half-lives work. This is 100% of, let's say, the C14 in a creature that just died. It died here at this mark. It has all of the C14 that it's going to have. Not taking in any new C14 as time goes on, it gets to a point where half of the C14 has turned into N14. Now we have 50% parent isotope, the C14, and 50% daughter isotope. That's 5,730 years to here. That is one half-life. And there is 50% of the original material after one half-life. Another 5,730 years after two half-lives, you have half of the half, which is 1/4 or 25% of the original material. After another half-life of 5,730 years, you have half of the half of the half. Half of 25 is 12.5. If you went on, 6.25. After 5 half-lives, there is only 3.125% of the original material. That's 5 times 5,730. And then you could find out exactly how long it has been since that thing died. Now, carbon-14 is good for everything, like I said, up to about 60,000 years, and then there's just no more carbon. So in order to find out how old something is by absolute age, that's maybe a Tyrannosaurus Rex that's way buried deep into the earth, they can't use the sediment that is all around and in the fossil, because sedimentary rock is just little pieces of other rock. So we need some new rock that had just been made, igneous rock that was lava and then hardened into igneous rock. They can take samples of uranium from that using the same method, looking at half-lives of uranium-235, which has a half-life of 700 million years, meaning from here to here is 700 million years, and then another, now we're up to 1.4 billion years, and on and on. They can do that with rock that is below or above, igneous rock that is below or above a fossil in sedimentary rock. These are the ways that scientists have been able to date rocks that are as old as 4.56 billion years old. They've taken samples from the moon, from meteorites that have fallen to the earth, and from rocks deep in the earth itself. I hope this has all been helpful, and I hope you have a great day. Love you. Bye.